And what kind of communication systems are there? There are multi-antenna systems, because a smartphone operates MIMO, but not only MIMO in the sense of multiple antennas for one standard, but there is a GPS antenna, there are Wi-Fi antennas, and all these systems have to be tested. And in the view to autonomous driving, you also have ITS-G5 systems where cars communicate with each other. And GNSS is a very big topic, because also for autonomous driving or for high precision farming, you want to autonomize farming vehicles, that they do it automatically. And what kind of test procedures do we have? So I mentioned the conductor test. You have some device under test. You unmount the antenna, you put a cable and a device tester. So you could connect a mobile phone with a cable to a base station and test the throughput. Additionally, you could include the radiation pattern, but if you imagine a smartphone, there is no antenna connector left. It's very small, everything is integrated, and you cannot put an antenna, a cable to the antenna port, and if you do so, you'd completely destroy the antenna pattern. There is another approach, which is called radiated two-stage, or we call it wireless cable. Why wireless cable? Because you have a device under test with certain antennas and antenna ports, and you have a shielded chamber with an over-the-air testing systems with multiple antennas. And now you superimpose antenna weights such that you address only a certain antenna but not the other antenna. So you create a virtual cable to only one antenna port, and with another set of weights you address exactly the other antenna port but not the first one. And why shall we do that? Because if you have multiple communication systems on a device under test, you might have interference. And with cables, you cannot consider interference. But if you have all devices there, so you can check if the LTE modem on the car is interfering to the GPS receiver or not. And my focus today is wavefield synthesis. So for wavefield synthesis, you don't need any calibration as you would need here, where you calibrate the wireless cables. In wavefield synthesis, you just put your device under test, which is a smartphone in this example, on a phantom head in a certain chamber. And in an area around these device under test, you have a sweet spot. And this means in this small area, you have conditions as you have outside. So you have plane wave conditions, which are created by superposition of certain elementary antenna waves. The only problem here is that you have a high hardware effort and a restricted device under test size. Because this area, you can see it here, where the wave is plane, is only here in this small area, and here you have some ripples. And this is what you want to realize. Just imagine a multi-element antenna, for example, a GNSS antenna for GPS or Galileo or GLONASS. You have certain satellites with scatterers and spoofers, and maybe a jammer that tries to disturb the GPS signal is moving around, and that's what you want to reproduce in the chamber, because field tests are expensive and are inaccurate, so you put everything in there. And by superposition of these waves of these antennas, you can recreate this propagation channel. The wavefield synthesis was at first realized in acoustics, and for example, you have a home cinema systems with surround loudspeakers, and there you have a very small sweet spot, which is the area where the acoustic experience is perfect. The problem is, if a person is here or here, it wouldn't have the same experience. Now, if you put a lot more loudspeakers and you do wavefield synthesis, then the sweet spot is much larger and it covers the whole area. And this is what we want to move from acoustics to electromagnetics. And here are some acoustic examples. This is how an acoustic setup looks like, which was already integrated in some large concert halls or theaters. And you might know this guy. And the one on the left is Karl-Heinz Brandenburg, the inventor of MP3, who also took part in the invention of wavefield synthesis for acoustics. And this is how it's done. You have a virtual source, a certain loudspeakers or antennas, and if you do it properly, then you can recreate this wave field here, which represents this wave, without having any wave coming from here. And this is the basis in theory in physics. It's the Huygens and Fresnel principle. And on the left side, you have a plane wave, a virtual plane wave, and some barrier. And on this barrier, in orange, is a small slit. And on a small slit, you have an emission of a circular plane wave. And if we now increase the number of slits, then you can see that the wave on the right-hand side converges to the wave on the left-hand side. So the wave gets plane if we have more and more slits, and if we are on a distance which is less than half lambda, then the wave looks the same as the original wave. And that's the magic behind. Now, how to do it? In math, the basis is the Kirchhoff-Helmholtz integral. It states that if you have some volume with a certain boundary and you have a virtual transmitter, you can prescribe the field on every point inside this volume by only knowing the field conditions on the boundary. So you don't need to know what's happening here or here. It's only necessary what is here. And these dots represent your antennas or loudspeakers, and then you can synthesize any field inside. And this integral is composed of monopole sources and dipole sources. And the result is that you have a certain field inside the volume and 0 outside. And now we can try to realize that. You have some virtual wave, and here is a small cut of a boundary. So here is the inside, and here is the original wave. And if we now apply these Kirchhoff-Helmholtz integral, we see that we have inside the reproduction of the wave, and outside there is nothing, it's 0. So this is nice, but to realize monopole and dipole sources at the same position is hard. So we would need different kinds of antennas at the same position. That's not easy. So we just remove one part and stick the monopoles or to dipoles, and then we have the same field inside again, but outside some mirror effect. But it's not a problem, because if we have a chamber with absorbers, we can absorb the field that goes to the back, and we have proper field conditions inside. Here you can see another drawing of it. These dots are the antennas, and in gray are the elementary waves. And in this small sweet spot area, they superimpose to have a very plain structure. These plane waves does not mean that we only want to generate plane waves, but we could also generate cylindrical waves or any wave we want. It's just the standard example for far field condition. And how about the number of antennas that we need? I showed that we need a distance of less than half of lambda. And here in this example, we have also the primary wave again. And these bars represent the antennas. And the green bars represent the active antennas. And if we have 24 and a distance of 1.3 lambda, the field inside doesn't look at all like the field that we want to produce. We could now increase the number of sources to go below lambda half, but then we need 64 sources, which is very expensive, because we need signal generators that operate phase coherently, and this is very expensive. And if you put the antennas close together, you have coupling effects that you don't want to have. What could you do? I was talking about the sweet spot. You define another area inside, and only in this area you force the wave field to be as you want it to be. And outside you don't matter, because your device under test is only here. And so you can get 24 sources which have a distance of 1.3 lambda, and you synthesize the field here properly. And why does this work? Because if you project the antennas from the outer antenna ring onto the boundary of the sweet spot, you can have this condition of lambda half. And in math, we do it like this. Inside our sweet spot, we define certain points. And these points, at these points, we want to have a certain electromagnetic field vector that we would have if we had the virtual source active here. And now we can tune the antenna weights in amplitude and phase, and to a certain superposition to produce this field. So we only need to know the relation between the antennas and the points inside. And if we know that, we can set up an equation. So our transfer matrix, x times some antenna weights, give us the target vector. And by solving it for the steering vector, we get the antenna weights to produce a certain wave field. in practice, this is our setup. I told you that we have very expensive hardware. Now we have 32 hardware channels that we can drive. And these are the signal generators. And behind the signal generators, you need signal processors to apply the antenna weights in a certain propagation channel from outside. And then you have some AD units to digitalize a base station signal, for example. And we also have a GPS signal emulator where we can put in GPS signals. And these are the two setups. This is a two-dimensional setup where we are able to emulate two-dimensional waves. And now we are working in this three-dimensional setup because, for example, if you think of satellite systems, you also need waves coming from higher elevations. And to calibrate the whole system, you have real cables, you have real hardware, which the hardware can drift, and you have non-ideal antennas. You need to calibrate these delay and phase and the attenuation somehow, and also the path loss between the antennas and the sweet spot. How do you do it? You take an electromagnetic field probe that you can move on the positions of these inside the sweet spot. And so you can measure on each point where the field has to be defined. You measure the influence of each antenna, and so you can get a measured transfer matrix to solve this equation system. And you want to know if the whole thing works. So I wanted to emulate a certain plane wave coming from this direction. This is a simulation. And in practice, I used this field probe again to move it around the sweet spot in a grid shape to see what happens and if I really have this plane wave conditions. So that's only a visual example, but in academia we want to have something more sophisticated. I used the aerovector, which is the difference, the error vector between the target and the synthesized field vector. And in the simulation, we achieved an average error of minus 35 dB, so the error is less than 1/1000. And in the measurement, it was slightly worse, but it's also in the same range, so we can say that this wavefield synthesis approach works in practice. And what kind of limitations do we have? I was saying that we have a restricted amount of numbers of antennas that we can drive, and we have a small sweet spot, and we are bound to certain frequencies. And the problem is you have the sweet spot diameter where you can synthesize a wave is less than this equation tells you. So the wavelength goes into the equation and the number of antennas. So this is a two-dimensional example. And if you think of a whole sphere that you have to cover with antennas, you need many more to cover the same surface. So here you have the square root of the number of antennas, and so you need more antennas to achieve the same sweet spot dimension. And for 32 antennas at 1.5 gigahertz, you would have 97 centimeters, but in 3D, on a hemispheric arrangement, there is only 40 centimeters where you can place your device under test. And if you raise the frequency, the whole situation gets worse. And if you go to millimeter waves, then you need a completely different approach. But for GNSS and 4G, it's a very good approach for testing. Now some examples what we can do with it. So we are dealing at the moment with jamming and spoofing experiments because this positioning or high precision positioning is very of much interest right now. And you have jamming and spoofing, and you have unintended or intended jamming. For example, truck drivers, they can buy these privacy protection devices that their boss doesn't know where they drive. Or you can spoof a signal and change the trajectory of a big ship. It was also proven that this is possible. And in military dimensions, you have very high power jammers where you can kill the GPS signal in kilometers. And that's what you don't want. Here in this jamming scenario, I wanted to compare 3 different types of antennas because we want to compare the performance of antenna or of a communication system. And these 3 antennas were an example with 4 elements and lambda over 6 distance, 6 elements, lambda over 3, and lambda over half. And additionally, I applied different signal processing schemes in the first type, I only use one element, which represents a single element receiver, and then I applied null steering and then beamforming, just as a comparison and as an academic example. So what else do you need? Some scenario. What should be realized? I have the device under test and the sky. Now I have some satellites around and a jammer that moves around. And depending on where the jammer is, certain satellite signals get jammed, or all of them. And in this case, I used the two-dimensional setup, where I have a ring with antennas. So I have to map these satellites and the jammer onto this ring, and the jammer then moves around a certain trajectory. Here is a plot of the movement. It's the co-elevation or the position on the ring. The satellites stay fixed because we have a very short scenario of 30 seconds, and then the jammer shows up and circulates twice around the device under test, and then we see what happens. So this is another drawing. Here is the antenna, and there's the antenna ring, and the jammer moves around, and we investigate the signal of one satellite, if the satellite is visible still or not. This is a schematic of the setup. Here is the device under test, and our general emulator, where I showed you the picture before. The input is a GPS emulator and the jamming signal. And on the output, we have a 6 channels recorder where we can record the outputs of the antenna and then do post-processing in MATLAB to easily compare the signals and also apply the beamforming or null steering. In GNSS and positioning, you're usually interested in the position of yourself or the time that you have, the accurate time. But if you investigate the quality of one satellite signal, you use the C/N0 metric. And there are different metrics, and I choose the moments method, which is very common and very easy to implement and hardware efficient. And here is a result for a comparison of the different signal processing schemes. This is the time evolution of the scenario, and here the jammer moves around the device under test, and at 12.8 and 70.8 signals, the jammer and the satellite signals are coincident, so they are at the same position, and if we are lucky, we still see the satellite, and if not, we have to use maybe other satellites. And the blue line is the case when I only use one single element antenna and do no signal post-processing at all. So you see that the signal drops when the jammer is present and when the jammer is at the same position, but it doesn't fade at all because in this academic example, the jammer was not that strong. We only wanted to compare the different types of signal processing. But if you apply null steering or beamforming, the signal drops, of course, because you mitigate a certain signal direction with your resulting beam pattern, and you don't see the jammer, but you don't see the GPS signal as well. So the signal vanishes, and then it shows up again when both incidence direction are not the same anymore. And to compare the different antennas, so you have small antennas, large antennas, and what's the difference? The difference is the antenna aperture, and if you have a larger antenna aperture, you can create smaller beams, and you can be more precise in your null steering and beamforming, and that's what you see here. If you use the small 4-element antenna, and look at this blue line, you see that the fade is very wide here. And if you look on the larger antennas, this fade is much smaller because the beam is more narrow and you are more precise in your beamforming, just as an example. And another thing is if you use beamforming, you superimpose the signals such that you have a higher carrier to noise ratio compared to the other or smaller antenna. The second example is spoofing. We wanted to check if a certain receiver and a certain antenna is able of mitigating a spoofing signal, detecting a spoofing signal and then still keeping its correct position and the correct time. And we constructed some scenario. The Spirant emulator creates 6 GPS satellites. So this is the original satellite constellation that goes to the receiver. And then we took these 6 satellite signals and applied some clock drift on them and added them so that we have a spoofing signal. So we didn't spoof the position of a receiver, but the time, because it's easier to show. And if the spoofing attack works, we see that the time of the receiver drifts from the time of the satellite emulator. And here in the center is the setup. We have the channel emulator, the spirant, satellite emulator, and at the end we compare the pulse per second in an oscilloscope. So the comparison of the receiver, of the GPS receiver, and the satellite emulator. And if these both pulses drift, then we see that this attack worked. And here's the result. In yellow we have the receiver PPS signal, and here we didn't do any spoofing countermeasure, so we see that the yellow curve slightly diverges. So the spoofing attack took place and was successful. But if we applied some anti-spoofing measures, we could show that it was not successful or that the signal post-processing worked. To conclude the talk, we have nowadays small antennas without antenna connectors, where we need some test procedures where we don't have to unmount the antenna and put cables. We, in the future, want to emulate millimeter waves. Therefore, we don't have any solution yet, but we are thinking about it. We have configurable antennas, which are kind of hard to test because you don't really can look into the antenna. We have electrically large systems and also multi-node systems that we want to test. So we have 1,000 nodes. How do they interact? It's hard to put 1,000 nodes into the chamber. We need some other measure. Yeah, and that's it for my talk. Thank you.
Thank you, Christopher. Any questions? I'm sure Benjamin or Marco Donald have some.
Can you give us some details on the synthesis process that you use to synthesize the field in the quiet area? How do you choose the weights of the antennas?
So here on this slide, you can see the math behind. And actually, you define a certain wave that you want to have inside, or a certain wave superposition that you want to have inside this sweet spot. And these waves you define by a simple plane wave approximation for a certain position O and a certain wave vector. And this is the basis for the synthesis. And you also define your field strength that you want to have. And that's what goes into the final equation to synthesize the wave field. You measure then with this field probe the relation between the antennas and the different points here, and then you can calculate the field. So it's in this equation, it's all a relative thing, and usually we do power calibration not afterwards, but in an iterative process. So we if we choose, for example, a GPS antenna and we emulate the signals, it's hard to define the power levels of signals that are below the noise level. So we measure with a GPS receiver how's the carrier to noise ratio, and we adapt it to realistic values that we have outside. That's the process.
More questions? Jutsu.
It's more a curiosity question about how do you generate your nice animation, the video at the beginning with wave field shaping. I'm very curious because I'm teaching array synthesis for master students, and if I could do something like this, they will be impressed.
Yeah, so actually it's done with MATLAB. It's some surface plots when you apply some shading, and then you save an image. You do the next frame, you change the surface plot, and you do the next frame, and you can make a video directly with MATLAB, but I use these single frames and use the movie maker of Microsoft to put it together. I could give you some example script if you like.
Impressive.
Yeah. Yeah, because electromagnetic fields are hard to visualize in your brain, so you need something that looks like water waves, and then it's easier.
More questions? Yes, no? So in this work, you don't have polarization, or you work only with amplitude. That's it?
Polarization is included.
Okay.
In the two-dimensional setup, we only work with vertical polarization because it was easier for the beginning to realize everything. But if you have a three-dimensional setup, you have to characterize all three spatial dimensions, and you have to measure all polarization vectors. Because if the antenna has a higher elevation, you have different projections of the field vectors.
And always working with a physical optics?
Yes.
Approximation, okay.
Until now.
Any further question now? Okay. Thank you.
Thank you.
Mario? Sorry, it's coffee break. See you soon.